Start recording. Good stuff. The key idea of dilutions is that it only involves adding water. And if you just add water, the moles of solute will stay the same. So if we look at our little picture here, whoa, what just happened there? That was crazy. If we look in our little container here, we have 1 liter and it contains 2 moles. Yes? Each of these little dots represents a mole. So the concentration of the dots is 2 moles in 1 liter, which is 2 moles per liter. Now, if we add 1 liter of water, the number of moles stays the same. Actually, I should just write moles stays the same. Number of moles stays the same. So you'll notice over here, nothing is changed in terms of the number of little black dots. They are still right there. We have just added 1 liter of water. So now instead of having 1 liter of water, now we have 2 liters of water. So if we want to find our new concentration, that's going to now be, instead of 2 moles in 1 liter, it's 2 moles in 2 liters. And if we have 2 moles in 2 liters, that's just equal to 1 mole per liter, right? So the trick is, basically what we do is number 1, we find the moles. And number 2, we divide by the final volume. Thank you. And here's an example where we do this without pictures, because obviously you're not going to be drawing pictures every time you do this. If we start with 2 liters of 9 molar solution, what does the word of mean? Of means multiply. So we're going to do that. We're going to multiply 2 liters times 9.0 moles per liter. And that gives us 18 moles. And then we dilute it to a final volume of 6 liters. So find your moles and then divide by your new volume. So 18 moles divided by 6 liters is 3 moles per liter, or 3 molar. Is good? Okay. So basically, you're going to do this. You're going to find the moles, and then you're going to divide the moles by the new volume. And I was just visited by some students from UBC today who came back during their reading break. And they said the biggest difference between high school and university is that you don't get enough time in university. So you are going to do these questions as fast as you possibly can, okay? You're considering this like a drill. You're going to go, and you're going to go hard, and you're going to go fast. Fast, 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 okay? Off you go. So if you would like to shorten the work and not show it in 2 lines, but rather in 1 line, here's what you're not allowed to do. So not this. You cannot say 0.025 liters times 12.0 moles per liter equals 300 moles, or sorry, 0.3 moles, 0.3 moles. That is a true statement, but what you cannot do is at this point go divided by 0.100 liters, because now you've made those 2 sides not equal. Does that make sense? Right? Because all of the yellow stuff is equal to the yellow stuff. It's not equal to the yellow stuff divided by 0.1. Yeah? So how you can get around that is you could write 0.025 liters times 12.0 moles per liter times 1 over 0.100 liters. Yes? That takes care of the division. And now on the other side of the equal sign, we'll have something that it is equal to, which will be 3.0 molar. Okay? There are a couple of other shortcuts you can do as well. Anyone interested in them? No, that's okay. I'm going to teach them anyway because I taught them to my morning block and they found them quite useful. You don't actually have to change milliliters into liters. Watch what happens here. We can say I have 50 milliliters of 12 molar, 12.0 moles per liter. And if I calculate that, I get 50 times 12 is 600. My liters cancel out and I'm left with millimoles. Yeah? Then I could take my 600, my concentration would be equals to 600 millimoles divided by my final volume, which is 100 milliliters. And now my millis cancel and I get 6 molar. You could, if you wanted to, do it all in one line. You could say I have 50 milliliters times 12 moles per liter times 1 over 100 milliliters. And if you see, your milliliters cancel out and all you're left with is moles per liter. So it's kind of a combination of this stuff over here and this one up here. And that is maybe one of the fastest ways to do it. We're also going to learn a couple other very quick ways to do it later. But if you want to start doing it a little bit quickly now, you can absolutely do that. Okay? Okay. Now, why does that have a profession? No, because that's the atomic mass, not the mass of the allowed to use the atomic mass. What did you just tell me about? What did you just tell me about these numbers? Oh, yes. Okay. Yes. Which is what you have. Write it down. So what's the mass? Yes. But I'm not sure which is what element. Well, how do you find the element? Look at from yes. You don't have to yes, you are fine. Elements can have different masses. That's actually what I do with every single question I do like most US stuff. And before I test, I only do US English. That's why for any to go through anything real quick, look at this science and that's also then charge negative. Yeah, that's true. What goes here, what goes at the top, and what goes down below. Wait, so that charge that is yes. What? You can do it separately. Right. Yeah, I don't mind. You can do it separately. You can do it together. However, it makes the most sense for you. Okay.
So before the volume is this time is after this one is and if you're finding the new concentration
Because you're adding those, right?
so you're finding the new concentration because it's
It's like getting
new more from this one.
Watch out when you get to question number 5. There's something a little bit different about it.
yeah.
Yes. What's different about question 5? Okay, page 59. This is another method if you prefer. This is actually my preferred method for doing this type of dilution. And I call it the noon method because we're working with our new concentration and our old concentration. So let's just take a look at this. So we have here our 1 liter of our 2 molar solution, and we add another liter of water to that, and we get a 1 molar solution. So if we look at what happened to our volume, the volume went from 1 liter to 2 liters. What happened to our volume? The volume was times 2. Our concentration went from 2 molar to 1 molar. What happened to our concentration? 2 molar to 1 molar.
Divided by 2.
Divided by 2. Or times a half. Yes? So what we have here is, this is what usually happens. Now, it's usually not as simple as we just double the volume. Usually it's more complicated than that. But we call this factor, where we have the 1 over 2, where did that 1 over 2 come from? That came from the 1 liters over the 2 liters. You start with 1 liter, you finish with 2 liters. And if we actually go back to 8.3a and take a look at the work here, we started with 0.25 liters and we finished with 0.1 liters. So we have 0.025 over 1. Yes? But now we're putting those two together, just like we're putting this one up here instead of having it separately. Okay? And this is what we call the dilution factor. It is our old volume over our new volume. And this is how we do the noon method, N-O-O-N. Our new concentration is equal to our old concentration times the old volume over the new volume. So that spells N-O-O-N. And how do you remember what it is? It's a new volume equals new concentration equals old concentration over new volume. Well, its concentration is equal to concentration times the volume over the volume. So it's concentration, concentration, volume, volume. And that is in alphabetical order. C comes before V. Yes? So new concentration, old concentration equals old volume over new volume. All right? You don't have to use this method. But if you like it, it can be really good. So in the last worksheet, we found the moles, and we did that by taking our old concentration and multiplying by our old volume. And that gave us our moles. And we can see we still have that in our new formula. We have our old concentration times our old volume, which is equal to the moles. And then what did we do with those moles? We divided them by the new volume. Okay, so we're taking our moles and dividing by the new volume. So it's new concentration, old conc times old volume over new volume. So here's an example. And once again, you can leave out you don't have to change things into liters. You can just leave them in milliliters. So we have 426 milliliters of water. That is added to 70 milliliters of 0.57 molar KBr. That is our old volume and our old concentration. So those are going to go right here. Yes? So what we do is we stick them in there, old concentration, old volume, over our new volume, and our new volume is not 426. It is 426 plus 70 gives us 496 because we added the water, so you have to define the total volume there. And we get 0.804. However, I think I've got the sig figs wrong there, so I need to fix this. That needs to be 0.080 molar. Okay. All right. So try these next three, quick as you can. See how fast you can do them.
Roll that up to this.
Yes. Here? Okay. Yes, I'll just be 1 second. I'm just going to press. Yes.
Other substance, but I just take like
We are now going to be on page. Oh, it doesn't want to move on me. Page 61, 61. No, not math. Page 61. Dilutions II. This one is how I got my job extracting DNA from salmon livers and trying to figure out which river the salmon came from, rather than counting herring larvae under a microscope for 4 months. So I got to do a job where I was like, okay, let's take the salmon liver, let's extract the DNA, let's chop it up with some restriction enzymes, and let's see if we can find a pattern to figure out which river that salmon came from. That was my job. My friend counted herring larvae. And why? Because I could do dilutions. Okay? So just FYI, it's a good skill to have for any sort of lab situation. So in this case, we're going to be looking at going the other way. What we have in the back room is we have solutions which are quite concentrated. We call this a stock solution. You can see here we have stock solutions. They are fairly high concentration. The nice thing about these is what we can do is we can take them and we can dilute them to other concentrations that are smaller. So if this was 2 molar, I could dilute it to 1 molar, or I could dilute it to 0.2 molar or 0.1 molar, anything that's smaller. And it just makes life a little bit easier than always having to take the solid and measure out the exact amount of the solid and then put it into the volumetric flask and do all the things that we know how to do now. Yes? So, we might have, thank you very much, we might have a concentrated solution of 10 molar hydrochloric acid. This would be our stock. And we might want a 1 molar concentration. Yes? This, what is the fraction of the concentration? If we're going from 10 molar to 1 molar, what is the fraction? 10 molar to 1 molar. 1/10. 1/10. So basically, we would need to raise the volume to 10 times what it was. Is good? Okay. If we wanted to get 0.01 molar, that's 1/100th. We would need to raise the volume 100 times. So basically 1 milliliter in 100, or 10 milliliters in a liter, or something like that, okay? And how we would do that, we would start with our stock solution. So here is our stock solution. That is our concentrated solution. And we would use our volumetric pipette to measure out a particular amount. Let's say in this case that we have in here 10 molar HCl. Okay? And let's say that this right here is 10 milliliters. Yes? Now, what I want to end up with at the end, my dilute solution, I want it to be 1 molar HCl. So I take my 10 milliliters of 10 molar HCl. What volume would I have to use here? What volume would I want this volumetric flask to be in order to get a 1 molar HCl concentration? Yes, I would want this to be a 100 milliliter flask. Yes, because I'm doing a 1 in 10 dilution. So 1 part HCl, 9 parts whatever, but I basically just go 10 in 100, okay? Now, that's kind of going at it backwards. What I really want to do is I really want to say, I would like to know how many moles are needed. How many moles do I need? And then I would say, what volume of my stock contains that many moles? Okay. And don't forget, this is very much the same as our other method of making solutions, which was to put the solid in the flask and then fill it with water to mark and then stopper it and invert to mix. So this one, instead of putting the solid in the flask, we put the stock in the flask. Yes? What kind of flask is that called? That is a... Oh, I heard it over there somewhere.
Volumetric.
Volumetric flask. So we would take our stock solution, we would put it into the volumetric flask, we would fill it to the line, and don't forget, when you get close, you would use a wash bottle and a eyedropper to get that final little bit so you don't go over the line by accident. And then we would put on a stopper, and then we would invert it to mix. Yes? So that's the procedure. Let's take a look at what the calculations would look like for that. All right. So in our calculations, we need to find, and we're still dealing with the fact that we have the same moles before as afterwards. So what we're going to do is we're going to say, how many moles do I want in my final solution? And then what volume of my stock contains that many moles? Yes? So we ask ourselves, find the number of moles you need in the final / diluted solution. What do we need? What are we trying to make here? And then you will figure out what volume of the stock solution contains that many moles. So again, what's the first step? It's find the moles. And in this case, you need to find then the volume. So let's look at a visual example of this. We want to make 2 liters of the little dots 2 molar. Yes? And we want our stock solution is 8 molar. So let's take a look. Here is our final diluted solution, and it's going to be 2 liters of 2 molar. So here we have 2 liters. And here I'm going to show the division between each liter. We have 1 liter and 1 liter. How many moles in each liter? I want 2 moles per liter. How many moles in each liter? Easy question. 2. Right? 2 moles in 1 liter gives me 2 molar. If I've got 2 liters, I'm going to need 2 moles in each liter, which gives me 4 moles in 2 liters. Yes? And now we ask ourselves, how much of the 8 molar stock will we need to get those? And how many moles are in here? There's 4 moles because we can count them. 1, 2, 3, 4. Now, if this is 1 liter of 8 molar, how many moles are in that 1 liter? 8. 1, 2, 3, 4, 5, 6, 7, 8. What volume of that solution do we need to get 4 moles of the dots? We need a half, right? But we're never going to draw these things out like this because that would drive us crazy. Yes? So instead of doing that, we're just going to do it with math. So find the moles that we need. So we know that we want 2 liters of 2 molar. So find the moles needed. So we have 2 liters of, of means times 2 moles per liter. So that's 4 moles. Now our stock solution, remember our stock solution is 8 moles per liter, and we want to find the volume of that. And we're going to be starting with our 4 moles. So we need to have moles on the bottom to cancel out and liters on the top. And because we're finding the volume of the stock solution, that's 8 moles per liter. So that's going to be 8 moles per liter. We do the math on that and we get 0.5 liters. Yes? How many milliliters would this be? 500 milliliters. Okay. So that's how you would do the math. You would find the moles and then you would calculate the volume. You can do this all in one line if you want to. Up to you whether you choose to do that or not. Now we are going to get a little more practical because tomorrow you guys are going to do a little mini lab. Okay, again, you're going to practice making a solution from scratch, but then you are going to dilute it. Okay, so let's think about this one. We're going to describe how to perform the dilution. So we need to measure out how much stock solution. How much stock solution do we need to measure out in this example? 500 milliliters. Okay, 500 milliliters. And we're going to use a specific size of a piece of equipment. And for this piece of equipment, you are going to choose either a graduated cylinder, okay, or you could choose a volumetric pipette. And just to give you some size perspective, this is a 25 milliliter volumetric pipette. 25. Imagine how big it would need to be to have 500 milliliters in it. Does that sound practical? No. Okay, so if you have a nice number like 25 or 10, like the ones we used for the titration, then a volumetric pipette is great because you can get a really precise measurement. But sometimes our volumes are just really big. So in that case, it would be much better to use, what's this called? A graduated cylinder. And you can have, if you happen to have a 500, you can use a 500 because that's perfect. But you could also use a 1,000 milliliter one and just fill it to the 500 mil mark. Yeah? Or if you didn't have that, you could measure 250 milliliters twice if you had only smaller ones. Okay, so we're going to use a 500 milliliter graduated cylinder. Once I've measured my 500 milliliters, we are wanting to make 2 liters of solution. What should I be pouring this into? What kind of thing? Look, 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 look. Well, there's water in there. You guys know, what do you make solutions in, generally? A volumetric glass. And guess what? 2 liters is a nice round number. Yes? Anytime we have a nice round number, chances are we can find a volumetric glass of that size. You'll notice I'm carrying this thing with 2 hands. Why would I be doing that? Because it's not heavy. I'm just paranoid about dropping it because these are expensive. Yes? And I don't want to be paying for a new one. Okay? So, and now that also because I am very clumsy, I am now going to just pretend I poured my stuff in there. I'm going to then add water to the line. What would I do next? Stopper it and invert to mix. Okay, I'm going to put these away now because I have a tendency to knock things off my desk. So I'm going to move these back over here out of my way. Okay. So, also just while we're at it, if you had 10 or 25 milliliters, you can use a volumetric pipette. Otherwise, you can always use a graduated cylinder. There's also a thing called a graduated pipette. How is this pipette different from the ones that you used?
There's no, it's more narrow and there's no part where there's like a bulge.
There's no part with a bulge. What a volumetric pipette would look like next to this is it would look like this. So this would be skinnier. And then it would have the bulbous. Okay, it would not look so wobbly. That's just because I can't draw. Okay, but they're actually relatively the same. They're not that different in terms of their thickness here, but this is much more narrow. Yes, when it's got that. So this is, you're able to be more precise, but you can only measure 10 milliliters with the volumetric pipette. But what if you wanted 8.7 milliliters? Then it would be better to have something that has all these little markings on it, yes? Okay. All right. So we would transfer our stock solution to we wanted 2 liters, so a 2 liter what? Volumetric flask. Now, what if you needed to make 10 liters of solution? Okay, we can find lots of nice volumetric flasks, 1,000 milliliters, 500, 250, 100. You might even be able to find a 5 liter, although we don't have any here at this school. If we want 10 liters of something, we are making it in one of these. Okay, you remember these from your lab? This is called a carboy. I don't know why. Maybe because when you go camping, you put it in your car and then you like open it. I don't know why it's called a carboy, but anyway, that's what it's called. And what I would do is, if I want to have approximately 0.1 molar NaOH, I might start with 1 molar NaOH. This mark right here, where did it go? There. There's a mark on it right here that says 10. That's 10 liters. Okay, so what I would do is I would measure out 1 liter of the 1 molar, pour it in, and then I would fill it to the 10 liter mark. How precise and accurate do you think this process is? Filling this huge thing with a big fat line. It's not very precise. So normally what we would do at that point is we would say, okay, I made an approximate solution. I would then probably titrate it with something where I made a solution very precisely so that I could figure out its precise concentration. Yes? So I would make maybe some oxalic acid is a really good one because it's a solid acid. I would measure out my solid acid. I would make maybe 100 milliliters of it, and then I would use it to titrate the NaOH to find out its exact concentration. Yeah. Okay? So yes, we do make them, but they're not like super precise, right? Because it's just not practical. I could spend a lot of time making 1 liter at a time, but again, that's not practical for the purposes of this lab, and nor is it necessary. Okay, so here we go. For irregular volumes, Say you needed 300 milliliters, you could use a 500 milliliter flask and fill it up to 300. You can use a carboy for bigger volumes. And one last thing, and that is about acids. If you have an acid, and it is concentrated, and you go and you put water in it, that mixing process is very exothermic. And what happens to water when you heat it a lot?
Evaporates.
Not only does it evaporate, but it
Expands.
boils. And what do things do when they boil? They spatter. Now, can you imagine if we had a concentrated acid and we added water to it and it spattered? How safe does that sound? Not very, because now we've got concentrated acid hither and yon. So instead, what we do is we put the water in first, or at least a lot of the water. So maybe we would fill up the volumetric flask halfway with water. And water has what we call a high heat capacity, which means that it is able to absorb a lot of heat before the temperature rises up. Okay? So if we have a lot of water present and we just sort of add the acid in slowly, we can prevent the temperature from raising too high too quickly. So we have a little mnemonic device to help you remember that. Do as you oughter. Whoops. Which is do as you oughta. Do as you oughta. Add acid to water. It's better if you do it with a New York accent. Yeah? Because then I'd actually do as you oughta. Add acid to water. And can you believe I found a little picture of an actual otter with little safety goggles on holding an Erlenmeyer flask? Like, how cute is that? Anyway, I was so pleased to have found this. I was like, anyway. Yes.
For the top where you use the little thing, that's supposed to say concentration.
Concentrated. Concentrated. So you don't want to add water to concentrated acid. You want to have water first, then add the acid, and then top up with water once you've got a more dilute acid. Yes? Australian Spence?
Yeah.
What? I became Australian? When?
There's in New York.
That was New York. Yeah. What would Australian be? Australian. Do as you order. Add acid to water. Kind of works. Do as you order. Add acid to water. It kind of works. Yeah. Okay. Now, these questions here is going to be your homework along with finishing up 8.1a and 8.3a and 8.3b. These go and walk you through step by step by step. If you want to do it all in one line and you're like, I don't want to do every single step by step by step, I just want to do it in one line, feel free. But if you're like, I would like to have my hand held, then go ahead and just follow these steps, okay? It walks you through numbers 1, 2, and 3, and then number 4, it's like, I've stopped holding your hand. You can just do it all in one step if you want to, or in several steps. Okay, so your homework is 8.3a, b, and c. I don't know why my pen is not working. And tomorrow, mini lab will make and dilute a solution. Hopefully the making part should be easy by now.
the